Okay. So, now as I said, most probable distribution. Now, you see we give two examples, 210 particle and we gave you an example of 2 particle. Now, we said that somehow we went to 210, it was fluctuating around 105, but not really going to 50 or 75. Why is that the case? Why all those possible distributions that could be possible, 1 209, 2 208, 3 207, like that, all possible, how many will be there? N possible. So, 210 possibilities, possible distributions are there. Why they were not happening? Why only one distributions, which is just half or most probable distributions, are surviving? We can see that from here. So, here we are plotting the W with respect to the number of W is the number of microstate for possible distributions. Let us say we can call that as N1. So, N1 in one box versus other. So, we are just plotting this function where W is factorial n by N1 factorial and n minus N1 factorial. We are plotting this particular quantity as W and plotting against N1. Now, what you see is that is pretty flat distributions when our n is equal to 10 particles. Yeah, it is 10 particle, and the peak, as you can see, is at 5. Now, let us go to the next one. Now, I am plotting 100 particle, and you see the peak is at 50. Again, it is peak is in the middle, but somehow the distribution has become narrower, is not it? Now, with respect to what it has become narrower? With respect to the percentage deviation. So, if you call that as half, then with respect to its half, it has narrowed down. Now, let us go to 1000 particle. Again, as you see, I am plotting the W. I will write the formula here itself, so that we can refer to it, n factorial by N1 factorial and n minus N1 factorial. This is the two level system number of microstates, right. So, here the n is 10, here the n is 100, here the n is 1000. It is picking up as at 500, as you can see, the most probable value or most probable distribution or most probable the maximum W or most probable value of the W is at in the middle when it is half at 500, and it has become much narrower even than the 100, right. Let us go to 10,000. Here n is 10,000. Again, peaking is at 5,000 and it has become much narrower. So, this 10,000 is just 10 to the power 4. Okay. We have to go to 19 more orders of magnitude in order to reach 10 to the power 23, which is just 1 mole of particles. Imagine what will happen to this particular graph. Even 0.00000001% deviation will be extremely small probability. So, therefore, we can safely say that it is the most probable distribution, one distribution for two level system which has half of particle is what is required to calculate the W, which means we say that our W most probable distribution is all possible distribution when n is large, because we do not need other one, because as you can see the graph drops here, we do not need the other W's, other values. So, see for example, n1 equal to 2000 is not there, no W almost for that, there is no W for even 4000, it drops just around 5000. If you plot at the percentage deviation, it will be much more clear. So, percentage deviation from n2 will be much more clear. So, according to the percentage deviation is not at all changing, which only means that it is the 5000, like for 10,000 particle is the 5000 which is most probable. So, that means half and half, it is most probable, and that is you need only that, and everything else will not be required at all. We will show you through the example. So, again number of ways that 50 heads can be obtained from 100 tosses, which is again 50 particle can be distributed in one box out of 100 particle, is the same thing, is 1.01 in 10 to the power 29. If I just do 2575, it will be 23, 6 orders of magnitude less. So, it is like the same situation, 50 heads out of 100 tosses is same as saying that I give 50 particle in this box and 50 particle in this box, and that has a W of this much. Now, if I say that okay, I give 25 particle in this box and 75 particle in this box, that has this many possibilities, 6 orders of magnitude less possibilities than this. So, this is our MPD, this is another distribution which is less probable. So, with large n more and more this will be prominent such that for a 1 mole particle the distribution will look like a line which we call as delta function, that is just a straight line, just one line, which means that only one value survives and everything else does not. So, one distribution is more than enough, and that is why we say that all possible so for n particle how many possible distributions? N, but all n minus 1 are not important, only one is important, and that is the most probable distribution. So, if we say that our entropy is Kb ln W MPD, actually entropy is Kb, entropy should be Kb ln W tot, but since our W tot is almost equal to W MPD, we only need one distributions, most probable distributions to calculate the entropy, and you will see that it has enormous implications to understand future things later on. We will show you that it is not possible for us to calculate all possible distributions for a realistic system. However, we can still calculate MPD, and since we know our most probable distribution, and since we know the most probable distribution is all that we require to calculate our entropy, we are safe. Had we required all possible distributions, we could not calculate entropy for realistic systems. We will show you that it is very important to know that most probable distribution is the only distribution that is required for us to calculate the entropy, and most probable distributions can be calculated for any realistic systems due to Boltzmann. We will come to that. Now, here you can see I am showing in Mathematica that how with a number of n's the distribution getting sharper and sharper, but I am going to show you some calculations in Mathematica as well. So, as you can see in Mathematica we have used Mathematica, there is a software in which we can calculate these big combination problems, and then we can plot that, and we have shown that how with the percentage deviation 0.5 as the number increases the distribution getting sharper and sharper. You see here we have used the relative deviation from the half. So, 0.5 the maximum is always maintained at this value, as you can see, but with n it is shrinking, and that is all is required. So, when the number becomes very large, here we have not used much larger like 10,000 or something. If it goes very high, then the distribution will be much sharper. Now, we can mathematically show that. We really do not have to rely on this graph to show you that the most probable distribution survives. So, here the W denotes some number of microstates for a particular distribution, meaning for n1 in one box and n minus n in another box. And we can show that W is maximum when n1 is half. We will first show that, and so why that is half, we can show that, and then all possible distributions, as we said, for an distinguishable particles in distinguishable boxes, all possible distribution is 2 to the power n. We have discussed that is all possibilities, and we will show that for large n this becomes equal to that Okay. So, we are going to show first that this W, this quantity W become maximum when n 1 becomes n by 2. So, we will need more space here and we are going to use this space here. W is n factorial by n 1 factorial and n minus n 1 factorial. Now, we have to maximize the W with respect to n 1, right. So, it is a problem of maximizing any function f x with respect to x, and what we did that in that function we say that if it is maximum, then d W with respect to d n 1 should be equal to 0, and that gives us either maxima or minima, and by doing the second derivative we figure out whether it is maximum or minimum. Here we are just going to do the derivations of W. Now, since this problem is associated with something called factorial, maximizing W is difficult, but we know that maximizing W is essentially same as maximizing ln of W. So, we are going to maximize ln of W with respect to n 1 and put it equal to 0. So, what is ln of W? Ln of W is then ln of n factorial by n 1 factorial and n minus n 1 factorial. So, that is the ln. Now, in this particular case we are going to use something called Starlings approximation. We are going to write it here, and that is true for large n. Remember, so it is not true for all possible n's, it is only true for large n. So, Starlings approximation says that ln n factorial is n ln n minus n. We need to use that, and I will show you using Mathematica that this quantity, that means ln n factorial divided by this right hand side n ln n minus n is approaching 1 when n becomes large. Since we deal with the situations of very large n, since I already specified, but that is for small n, most probable distribution is not equal to all possible distributions. Only for large n, most probable distribution is almost equal to all possible distribution. Therefore, we can use Stirling's approximation because we are working in the regime of large n only. So, let us simplify ln W then little bit. It is ln n factorial minus ln n 1 factorial minus ln n minus n 1 factorial, that is my ln W. So, I will simplify it further. So, ln W is equal to n ln n minus n, that is my first term. My second term then n 1 ln n 1 minus, instead of minus will be plus n 1, and my third term which is minus n minus n 1 ln n minus n 1 plus n minus n 1. So, now my W is complete. Now, what I am going to do is that I am going to take a derivative with respect to d ln W by d n 1. So, the derivative of this term is going to be 0 because n is a fixed quantity. So, first term is 0 minus second term is also 0. Now, the third term, now this term. So, this is a product. So, I can do as a product way n 1 into derivative of ln n 1 is 1 by n 1 minus ln n 1, because derivative of n 1 is 1. So, I am just doing a jump, but you can check it yourself. Now, derivative of n 1 is 1. Now, this quantity. Okay. Now, this quantity I have a minus here, this quantity, this term I have a minus. Now, this minus has n minus n 1. So, first one will give me 0 and second one will give me minus 1, and minus minus will actually become plus. So, plus was fine, ln n minus n 1. Now, I need to take a derivative of the second one. So, now I say n minus n 1 ln of this quantity right hand side, this particular quantity, which is 1 by n minus n 1, and then I have to take a derivative of the one that is here. So, that will be minus 1. Now, the last term plus, that will give me 0 minus 1. Now, let us write it down what we got. 0 minus 0 is 0. So, just I will not write it first two terms I will not write it, I will start from this term. So, this n 1 and this one cancels and gives me minus 1 minus ln n 1 plus 1 plus ln n minus n 1, this cancels and this minus cancels, give me plus 1 and minus 1. Let me see, minus 1 plus 1 cancels, minus 1 plus 1 cancels, giving me, I will have to have more space. So, I will use this side. So, del ln w by del n 1 is equal to minus ln n 1 plus ln n minus n 1, okay, which is, we know that in that case it is nothing but n minus n 1 by n 1, and that is 0. So, when is ln 0? When this quantity is 1. So, n minus n 1 by n 1 is equal to 1, which is n minus n 1 equal to n 1, which is n equal to 2 n 1 and n 1 equal to n by 2. So, we have seen that when n 1 equal to n by 2, then W will be maximum. So, now I will go back to the point where, so we have shown that this is, we have shown that WMPD, that means most probable distribution, that means the maximum value of W is when n equal to n 1. So, from here we get that if n 1 equal to n by 2, the W is called WMPD. Now, once we get that, we have to show that WMPD. So, WMPD is nothing but n C n by 2, that is nothing but 2 to the power n. So, let us do that. So, W tot equal to 2 to the power n, that is all possible distributions, right, n distinguishable particles, 2 distinguishable boxes, which, so we know that how many possibilities will be there, 2 to the power n, because first particle can be any of the 2 boxes 2 ways, second particle can be any of the 2 boxes 2 ways, like 2 to the power n. It is like coin tosses also. So, if I toss n coins, then the number of possible heads and tails, the string can be, there are 2 to the power n possibilities. Now, we are saying that MPD, the most probable situations will be when there will be half head and half tail, half particle on this side, half particle on that side, equivalent statement. And when the n is large, then it will be almost, it will be same. That means, basically all possibilities and half head, half tail are same, but that is very difficult to really imagine, and we are going to show that through our derivations that that is indeed the case. So, let us take from here ln of W tot, which is n ln 2. Now, ln of MPD, now first of all we write that MPD, most probable distribution, this is this and this is this. So, ln of WMPD is equal to ln of n factorial by n by 2 factorial multiplied by n by 2 factorial, equal to ln n factorial minus ln n by 2 factorial minus ln n by 2 factorial, which is ln n factorial minus 2 into ln n by 2 factorial. Now, again we are talking about large n, because it is not equal for small values of n, and therefore, you can use Starling's approximation. So, I will remind you Starling's approximation is ln n factorial is n ln n minus n, it is called Starling's approximation, as you have seen in my Mathematica file that they are actually same. So, now let us see. So, this is n ln n minus 2 n by 2 ln n by 2 minus n by 2. So, n ln n minus n minus n ln n by 2 minus minus plus n, cancels each other, I take n common, I get ln n by n by 2, which gives me n ln 2, is not it same as ln w dot, which means then ln of w dot is equal to ln of w MPD. So, therefore, w dot equal to w MPD when n is large. So, it clearly says that using one distribution, which is the most probable distribution, is enough to calculate the number of microstates and therefore, and in subsequently to calculate the entropy. This is extremely helpful. Without that, our life would have been difficult, and you will come to know later that why is that. So, the question is that we have considered that the particles have no interactions, and that is why they distribute equally. What if the particle would have had some interactions? And you are going to see later on that whether there is interaction between the particles or whether there is some preference of some boxes than the other box will actually change these statistics from n by 2 n by 2, or that means equal to something else, and that will become clear later on that how it is so.